There's a sign-up sheet which we are just leaving on the table over here. Please sign your name. So for our first talk today, we have Thang and who will talk about torsion growth of finite covers.
Thank you. I would like to thank the organizers for the invitation. So I'm going to talk about, well, the topic is very similar to what talk that I gave here about 4 years ago, and actually I did almost some progress on the problems that I considered at that time, and also the
Just speak in here.
okay. And I think the next talk of latent fields is also related to this talk. So let me first set the setting. So suppose X here is a finite CW complex. And I will consider a regular covering extender X here by some group. Gamma here is the group of Thang transformation. So this is a regular covering. Okay, now for every subgroup, if lambda is a subgroup of gamma, and I will assume that lambda is a finite index, I will look at the corresponding covering. So X sub lambda here is the corresponding covering of X. Corresponding to the group, so we have here, this is X sub lambda, cover this. Well, in general, I don't require lambda to be normal subgroup, so this covering here might not be a regular covering in general. But this one here, the big one here, is a regular covering. Okay. And the problem here is to look, we want to understand the asymptotic of the homology Hj x lambda z as, so I use here the notation lambda goes to 1, and I will explain what does it mean. Okay. So the growth rate or the asymptotic of the homology of finite covariance as lambda goes to 1. So before giving the precise definition of this, let me mention that problems like this have a long history. I think Cam Gordon is the first to ask about the growth rate of torsion invariant of knot complement. So this is also, so you look at cyclic covering of knot complement and ask questions about the growth rate of the torsion part of the homology. So that's Cam Gordon. So that is the few here. So, right here. I think it's around 1973, and made important contribution in 92. He proved, I think in 94, he proved an equality, while answering a question of Gromov on the growth rate of the Betti number, and I will precisely formulate the reason of Luke. And then later, Frobert generalized the case when the subgroup is not normal. Well, all these are related to the so-called L2 invariant of covering, of infinite covering. And among the audiences, there are many people who made contribution in these problems. So Mark made very influential work on the growth rate of homology and in particular connection of the growth rate homology with the property tau of groups. There was work of Silver and Julian. Important work on the growth rate of the covering of link complements. So I think that Stefan and so also had worked on the growth rate of this and
GEL.
GEL. LEL.
Say that for
Precise question.
Sorry, Stefan.
Oh, hell. That's right. All right, correct me.
Rambo. And many others. And lately also an important contribution was made by Bergeron and Venkatesh. Yeah, and many other people. Okay, so now let me explain what does it mean. I mean this notion of conversion to one. So let me denote by G the set of all subgroup lambda subgroup of gamma such that the index is finite. Yeah. And gamma n is a sequence of elements of this subgroup. So just a sequence of finite subgroups of finite index of gamma. So what does this mean? Well, before giving the definition, maybe let me give some example. So the first example is the one that can be easily comprehended. So suppose gamma, each element of the sequence is already a normal subgroup, and also gamma n plus 1 is a subgroup of gamma n. So this, we have a nested sequence of normal subgroups. Okay. Then our definition would say that this gamma n goes to 1 if and only if the intersection of this gamma n is the trivial group. Okay, so in this case, if you look at the corresponding covering, this is just a tower of coverings, and if the intersection of this is trivial, say that the tower covers to the total space. Okay, this is just, we have a tower covering. So this is the, I mean, if you, yeah, this is the simplest example of such a covering, convergence. The next one is, suppose you have sequence gamma n, which is, each element is still normal, but we don't require this nesting property. Okay, just each gamma n is a normal subgroup gamma. Then gamma n converges to 1 if and only if for every G, every element G in the group, gamma, G belongs to only a finite number of the lambda, of the gamma n. Okay. So G belongs to, at most, a finite, well, a finite number of gamma n. So it means that there exists a constant capital N such that if n is bigger than capital N, then G does not belong to lambda n.
Provided G does not equal 1.
Thank you. So this is a sense to say that if we take the intersection of lambda n, where n from m to infinity, and we take the, so this is the union, and then the intersection n from 1 to infinity, that is just the trivial. So this just say that if you look at the curvature, the injectivity radius of the curvature go to infinity. Okay. But again, I mean here I assume that gamma n here, each gamma n is the normal subgroup of the Leg transformation. Okay, and now let me really define the notion of convergence group here. So we say that, okay, but before that, let me introduce the following notion of trace. So there's a function we call trace on the group C gamma, the group ring QC, defined by the following in a very simple way. So this is C linear. So we need to define trace, so this trace gamma on an element G in gamma. And this is simply just 1. If G is the unit, 0, other ones. Okay, it's very simple. So you might wonder why we use this functional on this group ring. Actually, there is a theory of four Neumann algebra, and so this is just a remark. In many cases, say in the case of knot group, when gamma is I1 and 3 minus k, or in many cases. So in particular, if gamma is a knot group, well, I will assume that non-torus. Because torus knot will have center. In many cases, this is the only natural trace function on, well, C gamma. I'm not going to go into the details of this, what does it mean natural, but let me just say this. In a lot of cases, for example, in the case when gamma is the fundamental group of a non-torus knot, well, this group ring here can be extended to be a so-called four Neumann algebra. And that four Neumann algebra is a type 2-1, and it's the factor of type 2-1. And for a factor of type 2-1, there's only one trace. And this is that trace. I mean, this one can be extended to a trace on the corresponding four Neumann algebra. And that's and because it's the factor, so there's only one trace. You can also look at this trace as a generalization of the following case. Suppose gamma here, if gamma is a finite group, okay, then gamma acts on this by left regular representation. And so the Gx is equal to x if G is the identity. So it means that the trace gamma of identity would be equal to the dimension of this vector space, and Gx is never x for every G which is not identity and for every x which is gamma. So it means that the trace of the trace of the action, so maybe I write here the trace of the action is the trace of the action E on C gamma here is gamma, and then the trace of the action of G on C gamma here is 0. If G is not the identity. Okay? So if you normalize this trace, you get exactly this trace here for the infinite dimensional for infinite group. Okay, so this is a trace. I just want to convince that this is natural trace on the group. Okay, so now if lambda is a subgroup of finite index, if lambda is subgroup gamma and the index is finite, then there is a natural action of gamma on the set of cosets, or some left cosets. So gamma x on gamma over lambda. So this is, you have a representation of gamma on C of gamma over lambda. Okay, and now I can give the definition now. We say that lambda n equals to 1. So you should read this as if gamma n over lambda n converges to gamma over 1, which is gamma. And the convergence of this is just the trace convergence, with the trace of this converges to the trace of this. So this means that for every g in gamma, you look at the trace of g, the action of g on this vector space, the left coset vector space. And you have to normalize by the index. Okay, so sorry, the limit. So for every g in gamma, the limit when n's go to infinity, so this is lambda sub n here, and this is the index here, and that should be equal to the trace gamma of g. So that's the definition of the convergence here. So a sequence of subgroups converges to 1 if the trace of the quotient converges to the trace of the group. Okay. But the point is that many invariants in L2 theory are defined using this trace here. Okay. So the main question is, can you approximate L2 invariant using finite dimensional approximation? So this is very natural in the context of L2 invariant. And I think the part there in 97 was the first to look at this convergence here. And it turns out that this convergence, so this example, so actually I already gave 2 examples here, the first and the second. If you apply that definition to this sentence here, if gamma n is normal, then you can easily see that verified the conditions here. Okay. But so the third one is suppose that x here is a compact hyperbolic tree manifold. Three-dimensional. And gamma is the fundamental group. Okay. Then gamma n converges to 0 to 1 if and only if the corresponding covering x sub lambda n, the sequence converges to, so I put here ds to H3. This is from the Benjamin Schramm convergence that I think Nathan will explain next lecture. Okay, this is another notion of convergence. Benjamin Schramm, which is weaker than just the to say that the injectivity radius go to infinity. I mean the part that does not go to infinity should be small compared to the band. So that will be the precise definition. I think Nathan will explain in next lecture. And also another notion of convergence that that also attract a lot of attention later, especially in dynamical system people. It's the following. So you look at, so again, when lambda n here is a sequence of subgroup. So lambda n is this G finite index here. Then you have this, actually I already defined this, so this representation, so this is just the group, an action of gamma on the left coset. So I will write here a map from a homomorphism gram gamma to the set of permutation of gamma over lambda. this is a finite set. Okay, so this is actually a homomorphism. Okay, let me just mention this. For those who know what is a Sophie group, then lambda n converges to 1 if and only if this sequence sigma n here is a Sophie approximation of gamma. Okay, so in particular, gamma is a Sophie group. The Sophie group was introduced by Gromov in around 1999 as a generalization both of amenable group and residually finite group. And actually, this convergence here to say that the sequence that we have will, well, the definition, one of the definitions of Sophie group is that as a Sophie group is you can find a Sophie approximation to the group. Okay? And this definition say that then the sequence gamma n here converges to 1 if and only if it performs a Sophie's approximation to the group. Okay, so that is the convergence. And now let me formulate a result look and Farber. So let's return to the general setting. So we have here, so this x theta, x here, and gamma here. Well, x is a finite complex. So the theorem here of Rick and Farber is the following. If you take, so if lambda n, okay, so lambda n here is a sequence of finite index subgroup of gamma, and lambda n go to 1, then the limit, look at the corresponding covering and look at the homology, limit when n goes to infinity of the dimension, so it's with the rank or the Betti number, the rank of hj of x lambda d, and we define by the index, so this is gamma lambda n. So the first statement that the limit exists, okay, it's already non-trivial. The limit exists and is equal to the so-called N2 Betti number, which is an N2 invariant. So the J2 of the corresponding covering here. So for every covering like this, you can define the so-called the N2 Betti number. Yes?
When you say rank of the homology, is that the rank of the free part or the number of generators you need to generate the whole thing?
Okay, so I use here the usual rank. So it's yeah, rank of the free part. Yeah. Okay, it's just the Betti number. So maybe okay, rank Z. Okay, rank Z of that. Is that clear? Rank Z of a finite generally available. This is finitely generally available. So rank Z of that. Okay, so maybe I should mention that the inequality was first observed by Gashdan a long time ago, and then Gromov came and asked the question whether you have equality. Okay, at least in the case when you have a normal subgroup, and then the case when lambda n are normal was proved by Luc in '94. And then Farber came and defined the more that more general convergence. So the general case was proved by Farber in I think '97. So that settled the question about the asymptotics of the Betti number of finite covering. Well, maybe I forgot to mention that if you have a sequence, I mean, it's just an exercise. If there exists a sequence of subgroup of finite index so that such that lambda n goes to 1, then the group must be residually finite. That's an easy, it's not very difficult. Okay, so we have this result here. The question is, so here we take the rank of the group. So Hj of x lambda z. We have the free part, so you have the z to the bj of lambda, and you have the torsion part. So this is torsion z of Hj of x z, x lambda here. And let me note the torsion part, the size of the torsion part. So T sub j, which depends on the subgroup lambda, but the size of the torsion part is so torsion z of Hj x lambda z. Okay. Number of elements. Finite. So the question now is about the growth rate. So what would be limit when n's go to infinity of log of tj lambda over the index. So this is gamma lambda n. Okay, so that is very natural. Okay, if you look at the so here we have the results concerning growth rate of the Betti number, and this is the same question for the torsion part. And it turns out that this is much more different than the question about the growth rate of the Betti number. I should mention that in the theory, in algebraic dynamics, people also look at something very similar to this. Okay? They count the number of periodic points that's related to entropy, and the entropy is related to, well, actually, the number of periodic points is closely related to the torsion number here. And they also want to show that limit like this would be equal to the entropy of the corresponding dynamical system. Okay, so they establish some reasons in this direction, but actually I had to use one of their reasons in order to establish a theory in a reason in topology. Okay, so let me now look at the case of three manifolds. So now X is an orientable irreducible three manifold with toroidal boundary. Okay. In this case, you can define the volume, hyperbolic volume of X. So you first use the JSJ decomposition. So X is union of the thick part and the thin part. While you use the collection of toroid JSJ decomposition to pieces, the thick part consists of the hyperbolic pieces, and the thin part is just the fiber pieces. Okay, and then we define the volume of X to be the volume of the hyperbolic volume of the thick part. Okay. Another way to define this volume is to use the Gromov norm, because the Gromov norm is proportional to this. So I think it's equal to the Gromov norm of X divided by V3, right? The volume of the regular ideal tetrahedron. And then we have the following result. So the theorem. Chang would say that suppose you have a sequence lambda n in G and lambda n go to 1, then the growth rate, well, I cannot prove the existence of the growth rate of the torsion part, but at least the upper limit, so this is n go to infinity. If I take log of, this is T1 of lambda n, divided by the index, so this is less than or equal to the volume of x over 6 pi. So this is something very similar to the Gaussian inequality, but for the torsion part case. Well, so recall that this is just the torsion part of the first homology. For the first, I mean, T0 and T2 just trivial, so you don't need to bother about. In this case, you have just the only non-trivial one is just T1. That's less than or equal to volume of x over 6 pi. So in particular, if volume x is equal to 0, then certainly you have identity because this one is non-negative. So then you have identity here for the reason. For example, if you take the complement of a torus knot, then you have identity. The growth rate of the homology in any covering sequence will be sublinear in this case. Or you take the log, so it's sub-exponential. So maybe I formulate this before this one. So the upper limit, lambda is in G, and lambda is equal to 1 of T1 for log of T1 of lambda over the index is less than or equal to volume of x over 6.
Are you taking lambda to be the full fundamental group or some subgroup?
So G here is a set of all finite index subgroups.
Right.
Okay.
In the original setup, lambda could be any normal subgroup of the fundamental groups. Is it?
No, in the original setup, lambda is just a subgroup of finite index, not necessarily normal.
Sorry, gamma, capital gamma.
Capital gamma is just any discrete group. Okay, and you have a regular covering.
So it does not need to be, capital gamma does not need to be the full fundamental group.
No.
It was converging to 1. You're taking the ellipse loop as it goes to 1, so
This lambda is subgroup of gamma, which is go to 1, means that the corresponding curve go to that curve, go to the extender. But extender may not be the universal covering of x. So we can reformulate this theorem in this form here. Okay? And so I made the conjecture that I made a few years ago was that the limit, well, certainly, let me put here, G n here is a set of normal subgroups of finite index. So lambda is still in G, but lambda is normal in gamma. Okay? Then this one certainly stronger than the statement that the upper limit of lambda is in G normal, then I go to 1 of log of T1 lambda over gamma, the index less than or equal to the volume of x over 6 pi. So this statement is stronger than this one because this is just a subset of this. Okay? But I want to make conjecture that we have equality both here and here. And the conjecture here is, we have to reverse the order. The conjecture here is stronger than that one here because this sense is bigger and you are looking at upper limit. Okay. Well, so this strong conjecture, well, actually this is the one that I made about, I mentioned the talk 4 years ago here. Okay. But because I cannot make any progress on this, I make it within the weaker. This one. But as I say, this is stronger than this statement. Because the set is allowed to be bigger. Okay, I allow no normal covering. And also because it's interesting because it's related to the BS convergence and also Sophie groups and so on. So I think that that extension is simply very appropriate. Okay, so conjecture. So we have equality both in here, so in here, and so here. Well, certainly conjecture 1 will influence conjecture 2. I should mention that there are similar conjecture and independently formulated by, well, similar but still not the same, very well closely related to this, independently formulated by Bergeron and Venkatesh and also by Luke. And similar. And Luke also told me that he talked about this something like 20 years ago, although he never really published his, well, and he's an expert in L2 invariance, and he made already, I mean, the theorem about the growth of bad numbers. So certainly he talked about the growth of torsion. And there's some reasons where we do have equality of this type made by Bergeron and Venkatesh, and also in the work of Werner Müller. However, in these reasons, in this work, they use the non-trivial local system, I mean representation which are not unitary, and what we are considering here unitary representation. And somehow unitary representations are more difficult than non-unitary representations. I don't know why. I mean, usually unitary representations are easier than non-unitary representations, but I mean, for example, in the proof of Müller, he using non-unitary. One thing is that with non-unitary representation, you can move away from the difficult part in the spectrum, and then use some analytic gadgets to get the result. But for unitary representations, when the difficult part is well, the spectrum concentrates on the unit circle, and somehow it's extremely different. Okay, so that's all concerning three manifolds, and I think that Nathan will tell you some interesting reasons concerning three manifolds later. So let me now focus on the case of abelian curve. Again, here you have a covering. Gamma here is now just z to the n. Or typically, an example is if you look at a ring complement, okay, and you look at the maximal universal abelian covering, and you have this picture here. Okay, you have a abelian covering here. So x here is a finite CW complex, and there's an action of z to the n of this x theta here. So for example, if you look at hj of x theta z, then h of this is a z to the n model. Yeah. So h of this is a z to the n model. So it's also an R model where R here is the group ring ZZ to the n. And I will identify this with the ring of Laurent polynomial. You have the group ring of Z to the n, and we identify that with the ring of Laurent polynomial. And the homology of this H is just a model over this ring here. And now in this case, a lot of things would be simpler because this ring is, well, relatively simple. So it's a unit factorization domain, and it's Noetherian. Okay. So let me recall a few facts about model over this ring here. Particularly, what is the Alexander polynomial of model over this ring. Let me just first reformulate the convergence here. So lambda here, a subset, a subgroup of Z to the n. Of finite indexes mean that lambda, the rank of lambda, so lambda must also be isomorphic to Z to the n. You have a subgroup of finite index. And lambda goes to 1. Lambda n, oh, this is bad. Lambda k goes to 1. If and only if, well, if you look at the distance, so this is just, we take the limit when k goes to infinity, the minimum of the distance x in lambda n minus 0 here will go to infinity. Okay, so this convergence here corresponds to just the fact that if you look at the sequence of lattices in Z to the n, in each lattice you look at the closest point, the point that's closest to the origin, and so that point, the length of that point should go to infinity. Okay, to run this convergence. Okay. So now suppose M here is an R model. I will always assume that finitely generated. And now M will have a presentation matrix. What does this mean? Well, M here is finitely generated, so I have a surjective, some Rk mapped to M. I have a surjective map from a free, R to k to M. Okay, and then the kernel can be again mapped onto by another free one. So I have here some RL mapped to this here. Okay? And so I will have a map here. This map is given by a matrix A. So A here is a matrix. Is an L by K matrix. So I will write multiplication on the right here. Okay, so it's an L by K matrix. And I can always assume that L is bigger than L onto K by adding just 0 to the some 0 rows. Okay, it doesn't change anything. Okay. And then the Alexander polynomial, so delta J of M is defined to be the GCD of all the K minus J by K minus J minor of the matrix A. So A here is a matrix of sign L by K with coefficient in R, with entries in the ring R. So delta J of M, these are called Alexander polynomials of M, defined to be the GCD of K minus J times K minus J minus of A. Okay. You can easily say that delta J plus 1 divides delta J, and so on, until you get to delta 0, and you can put here delta minus 1 is always 0. And similarly here, you have the biggest one will be delta K, And the next one should be 1. Okay, so we have sequence of Alexander polynomial, which this one divides the next one, and so on. I mean, if R is equal to Z or any PID, then the sequence length J from 1 to K totally determines the model M. Well, actually, this called, I think it's called switch factors of the abelian group. I mean, if R is Z, M is just finitely generated abelian group, and then remember you have that M is equal to Z to the some Betti number plus Z over Sj, J from 1 to some K, where S1 divides S2 and so on by Sk. Okay, so this is the structure theorem of finitely abelian group, and this length J here can be easily determine the whole S1, S2, and so on. Okay, so this is the case when you have where R is Z. In general, so when R here is the ring of Laurent polynomial, the sequence of Alexander polynomials do not determine R, the model M. For example, in this case here, if delta 0 is equal to 1, then M is simply 0 in the case of over Z. If delta 0 is simply, well, delta 0 is 1, then M is equal to 0. Okay? But in this case, delta 0 is 1, M is still not 0, and might not be 0. And actually, there's a notion for this called pseudo 0 mod. Okay. If delta 0 is 1, then M is called pseudo 0. Okay, so that is the Alexander polynomial of the model. Well, there's some simple properties. Well, certainly when I define this, I had to use a presentation matrix A, but it's not different to show that the Alexander polynomial do not depend on the presentation matrix. Well, so delta 0 of M is called the order, also called the order of M. So if this is because if R is equal to Z, then delta 0 of M, in this case M is just a finitely generated abelian group, and this is equal to just the size of M. If M is finite, then 0 if M is infinite. Okay. When you take, in the case when the ring R is just a PID or just Z, then delta 0 is exactly the size of M. Or again, I mean, when we define this, delta J is defined up to units in the ring R because we take GCD of several things, so it's defined up to units. Okay, and now I can also define the rank of M to be the dimension over the fractional field of R of M we cancel with FR over R. So FR here is the fractional field of M. Sorry, of R. Okay, then you can easily show that J of M is equal to 0 if J is less than the rank of M, so I'm using R, and then delta J plus R of M will be the same as delta J of the torsion part of M. So actually you have just a shift. I mean, the sequence of Alexander polynomials here of a model is the same as that of the torsion part. You have a sheet by the rank. Okay, so that is the Alexander polynomial, and so I will denote by delta of m to be delta r of m. That would be the first non-trivial Alexander polynomial. So we have here in n, and we have here delta r plus 1 of m divided delta r of m divided delta r minus 1 of m, and so on. And actually all these are 0 here. And this is the first one that will be non-zero. The sequence of Alexander polynomial. If r here is the rank of n, delta r of n will be the first one that's non-zero. And we know this by delta of n. So that is the Alexander polynomial. Okay, and now let me find the last page before I can formulate reasons. So, suppose, so what's the Mahler measure? Suppose I have a polynomial f in Z of T1 to Tn, well, so in R, and I assume that f is not equal to 0, then the Mahler measure of f, what I find is the additive Mahler measure, so I take integral over Tn of log f of z is sigma. So Tn here is the n-dimensional torus, so it's the set of all d1 and dn in C to dn, such that the absolute value of each component is 1. And the sigma here, so this is a simple, a compact Lie group, and the sigma here is the normalized Haar measure. So the only invariant measure is that the total volume of Tn should be 1.
That's Tn minus 1. Right? Since it's a subset of
C to the n.
Oh, C.
C to the n, and each component has absolute value 1. Has.
Oh, okay.
Okay, so that's just n copies of S1. And did the Mahler measure? Okay, so now I can formulate. So let me recall that x theta to x here is a covering by with z to the n the group of X transformation. Okay, then limit when lambda go to 1, lambda in the subgroup of finite index of I take log of the torsion part of x lambda, and I divide by the index. This is z to the n lambda. Well, actually, to say that the upper limit is equal to the Mahler measure of the Alexander polynomial, the first non-zero Alexander polynomial of the corresponding j. So if we take j here, take the xj of the universal, not universal, of the covering z. Well, because this is an R model. This is an R model, so you can define the Alexander polynomial. You take the Mahler measure of that, and then the upper limit of this of the log of the torsion part over the index is equal to the Mahler measure of that Alexander polynomial. So maybe this part A and this part B. So we want to remove this upper limit here, one great limit. Okay. So the upper limit can be replaced by an ordinary limit if we have the following. Now, t to the n here is an n-dimensional real manifold, okay? And you look at the set of 0 of this Alexander polynomial, that aj of x theta, 0 of this on this one, in general, we have dimension n minus 1, okay? But if the dimension is less than the strictly less than n minus 1, okay? Then in that case, we can replace the upper limit by an ordinary limit. Okay? So in this case, we have just the full result in this case. Okay? And I should mention that in order to prove this, I have to use results of Schmidt and Lee, Schmidt and Verbitsky in dynamical system and some Bourbaki theory of pseudo isomorphism, and also so this is and also the theory of torsion points. Torsion points on algebraic sets. So this is known as the Manin-Mumford principle for this case. And in the case when x is a complement of the link, and h1 of x theta z is an R model, is an R torsion, is a torsion R model. The result was established by Silver and Williams. And actually they asked if this one is not a torsion model, then whether we have equality. But actually they ask more, they also ask for the equality without this upper limit here. So this is some generalization of Silver and Williams to the case when the model is not a torsion model. Now let me just mention one number theory problem that is related to this question here. And it turns out that it's quite non-trivial. So this is a conjecture. So limit, upper limit can be replaced by ordinary limit if we can prove the following conjecture. Suppose f is a polynomial with integer coefficients. Then there exists a constant c such that if zeta 1, zeta n belong to the set mu satisfies zeta j to be d equal to 1. So it's not just a d root of unity. Then either f of this c is equal to 0, or the absolute value of this must be bigger than 1 over d to the c. Okay? So that you look at the roots of unity of order d and you plug in this one here. It's either 0 or it must be somehow far from 0 by this one here. Okay? So let me mention that this when n is equal to 1, this is a classical result of Genfeld and also Baker, well, Baker mainly for this reason. I mean, Benson did some approximation to variable, and Baker generalized to n variable, and he got Fields medal for that work. But all this is enough only to prove the conjecture for when the case when n is equal to 1. Okay, so let me give you an exercise. Prove the conjecture for the case, simplest case, when you have a linear form. And linear is very simple, just sum of xn, xj, okay, from 1 to n. Okay. What do you think? Is this easy or difficult? I mean, if you have just a sum of proof, well, actually, it's the RG here, and the exercise should show the conjecture. So, I mean, and these two are equivalent. If you can prove just the conjecture for this simple linear form, you can prove the general conjecture. Okay. But as I know, this is a well-known open problem in number theory. Well, so the exercise just to show that if you can prove the conjecture for this case, you can prove the conjecture for this case. Okay, I mean, I ran over time. Thank you for listening.